Hello everyone. Today we are going to see the topic in embedded system, nothing but 5-stage pipelining architecture. I am Vanitha K, Assistant Professor working in the Department of Electronics and Communication Engineering at K.S. Rangaswamy College of Technology. So what is pipelining? Pipelining is an implementation technique where multiple instructions are overlapped in execution. So each pipeline is divided into different stages, nothing but fetch, decode, execute in 3-stage pipelining. As well as we are going to see what are the different stages of the 5-stage pipelining. So instructions are connected to one to the next to form a pipe. Instructions enter at one end, progress through the stages, and exit at the other end. What is the use of this pipelining? Pipelining will be used to speed up the execution by fetching the next instruction while the current instruction is in execution. So this is the architecture of 5-stage pipeline, where we have 5 different stages: fetch, instruction decode, execute, buffer and data, and write back. 5-stage pipelining. So in order to improve the performance, to get the higher performance is the demand of nowadays life. So in order to produce your ARM cores in a cost effective manner and to increase the performance, let us consider the formula, that is T. Time is the T required to execute a given program, where T is equal to N instruction into CPI divided by F clock. What is N instruction? N instruction is the number of ARM instructions executed in the course of the program. What is CPI? CPI is the average number of clock cycles per instruction. Then F clock is the processor clock frequency. How to improve the processor performance? So how to improve the performance? How to reduce the time taken by the processor to reduce the number of instructions in a program? So by increasing CPI and by increasing F clock and by reducing CPI. So reduce the average number of clock cycles per instruction and increase the clock rate. What is 5-stage pipelining architecture? So we divide the entire stage of instruction execution into 5 components rather than 3 components will be used in 3-stage pipelining architecture. In order to, moreover, it uses this 5-stage pipelining architecture, improves the performance by having separate instruction and data memories, allowing significant reduction in the core CPI. So this, where it is implemented, it is employed in ARM9 TDMI, where we have 3 source operands read ports and 2 write ports in the register file, and which will be included with address incrementing hardware to execute the stage to support load and store multiple operations. So the 5 different stages are fetch, decode, execute, buffer and data, and write back. What is fetch? We are fetching the instruction from memory and place it in the pipeline. Decode, the instructions are decoded and the register operands are read from the register file. Next, execute. We are performing execution operation by shifting the operand, and the result is stored. ALU result is generated. So if the instruction is a load or store instruction, memory address is computed in the ALU. So what is buffer and data? So if you want to use it as a data memory, so data memory is accessed if required. Otherwise, the result of arithmetic operations will be stored in will be buffered for 1 clock cycle. Write back. So write back in the sense, finally the result will be stored in the register file, destination register file. What is data forwarding in the 5-stage pipelining? Data dependencies arises when the instruction needs to use the result of one of its predecessors. For example, so data will be moved to stage by stage if you use LDR and add instruction. So here you have 2 more registers. The result of the arithmetic operations will be stored in this Rn. So load Rn with somewhere. Immediately you have to use this Rn with some other register, and finally you store the result of addition operation of these two in the R2 register. So which involves the result of LDR will be that is Rn will be available in the write back stage, but we need this add instruction, add instruction Rn in the decode stage, so which involves some data dependencies will slow down your processor, so slow down your performance. How to the only way to avoid the stall is to encourage the compiler not to put the dependent instruction immediately after the load instruction. So now we have to, here the dependent instruction is add, this Rn is available add immediately after the LDR, so we need to avoid these kinds of things. So from this stalling data dependencies, we have to know pipeline hazards. What are the different types of hazards? Data hazard, control hazards, and structural hazards. So data hazards is nothing but data, that is instruction uses a result of previous instruction. Control hazards, you move the control to some other location. So the location of an instruction depends on previous instruction. Structural hazards, two instructions need to access same resources. So data hazard example, when you see the instruction add instruction R1, R2, R3, the result of R2 and R3 will be available into R1 in the write back stage. Immediately this R1 must be added with R5 and the result will be available in the R4 stage, in the sense you use R1 immediately in the decode stage. So which will be the distance between the write back and instruction decode stage will be 2, that is execution memory stage. We need to make this instruction to be the result immediately available to write back result will be available to the instruction decode stage. How to make it this possible? By means of this stalling. We use stalling. Overcome these hazards, we use stalling, but it will slow down the process by doing nothing while waiting for the result. So add R1, R2 and R3. Stall, we use stalling stage by stage. So instruction fetch, execute, memory and write back stage. So only after 3 stalling only, when you put sub instruction and the result of R1 operation to be available in the decode stage immediately after the write back stage, so we use stalling. So in this case, in this way we can avoid the hazards by means of this stalling. Thank you. We have got the overall idea about 5 stages, what are the different 5 stages of pipelining architecture, where we employ this, how to improve the performance. Thank you.